Hello, everyone. Welcome to the Data Festival online reinforcement learning track. I'm Shangtong Zhang from University of Oxford. Today, I'm going to share my recent work on off-policy evaluation. So I will start with a brief introduction to reinforcement learning. Then I will go to the topic of policy evaluation. Reinforcement learning usually models the agent-environment interaction as a Markov decision process. So here we have an agent, and an environment. The agent keeps the interaction with the environment. At time step t, the agent is at a state st. Then it selects an action at according to a policy pi. So the environment will receive the action and execute the action. Then the environment will emit a reward rt+1 according to the reward function r, and leads the agent to the next state st+1 according to a transition kernel p. In reinforcement learning, we usually assume that the reward function r and the transition kernel p are unknown. All we have is the sample state st, reward rt, and action at, and we want to learn from those samples. There are two basic tasks in reinforcement learning. One is policy evaluation. The idea of policy evaluation is to estimate the performance metric of a policy. So we can first define a random variable gt, which we call return. So you can say gt is the sum of the discounted future reward. Here we need to introduce a discount factor gamma, which is smaller than 1. So gt describes the return that an agent can get in the future. And with the help of this random variable gt, we can define the value function, which is the expectation of the return. So the value function vpi at state s describes the expected total rewards that an agent can get, starting from the state st and following the policy pi. So in this talk, I will use function and vector interchangeably. So here vpi is a function. I will also use vpi to denote a vector lying in this high-dimensional vector space. Typically, we consider two performance metrics to measure the performance of a policy. The first metric is expected total rewards. Here I use eta gamma pi to denote the expected total reward. So the idea is very simple. We use this metric to measure the total reward an agent can get, starting from the initial distribution rho0. So basically, we just take the expectation of vpi s0 with respect to the initial state distribution rho0. And if we consider a vector form, we can write this expected total rewards in expectation. So it's the inner product of rho0 transpose and vpi. Another popular performance metric is the average reward. We use eta 1 pi to denote the average reward of the policy pi. The idea is also very simple. We first select an interval capital T, then we compute the average reward that the agent get in this interval. And finally, we let t go to infinity. So the average reward measures the rate that an agent gets in environment. Another basic task in reinforcement learning is control, where we want to find a policy to maximize a performance metric. So particularly, we want to find the pi star to maximize the eta pi. So here, eta pi can be any performance metric. It can be either expected total rewards or average rewards. But in this talk, I will mainly focus on policy evaluation. Reinforcement learning algorithms can be classified into on-policy learning and off-policy learning. So on-policy learning uses the policy being learned for data collection. So the idea is that we are interested in a policy, let's say pi, then we can actually execute the policy pi and get some samples like a state, action, reward, trajectory. Given those trajectories, we then estimate the performance of the policy pi. So this is on-policy learning. The other learning paradigm is off-policy learning, where we use behavior policy for data collection. So here we will have two policies. One policy is the policy we are interested in. Let's say pi, so we want to know the performance of the policy pi. So we will call pi the target policy. The other policy is the behavior policy mu. So we use the behavior policy mu to collect data. So here at the time step ST, the agent will select action AT according to the behavior policy mu. So this is different from the on-policy setting, where the action selection is done according to the policy pi. So although we select action according to policy mu, we are interested in the policy pi. So there are two different policies, and this is the off-policy learning setting. Off-policy learning has many advantages. For example, off-policy learning is safer than on-policy learning. Let's say if we have a very dangerous policy and we want to know the performance of that policy, so of course we don't want to actually execute that policy because then it may yield unexpected loss. But if we have off-policy learning algorithm, we can evaluate the performance of that dangerous policy with some data collected by some safe policies. In this way, we can achieve our goal of evaluating an unknown policy while being safe. Off-policy learning is also data efficient. Let's say in on-policy learning setting, if we want to know the performance of a policy, we need to actually execute that policy in the environment, which can be very slow. But if we want to know, let's say if we want to know the performance of 10 policies, then we need to execute those 10 policies one by one in your environment, which is not very data efficient. But if we have off-policy learning algorithm and we want to know the performance of 10 different target policies, all we need is to execute a single behavior policy and use the data collected by that single behavior policy to estimate the performance of those 10 different target policies. So in this way, we can achieve great data efficiency. Of course, off-policy learning has some disadvantages. For example, off-policy learning is very unstable. This is mainly because we have two policies, target policy and behavior policy, and they are different. Now let's go to off-policy evaluation. So distribution mismatch is a major challenge in off-policy learning. To understand this, we can rewrite the performance metric in the form of expectation. So let's first define the normalized discounted state variation. So this distribution d pi gamma. The idea of d pi gamma is just to count the state variation. So we have this summation of variation probability. Then we discount them by gamma to t because our objective or our performance metric is discounted in this way. So we also discount the state variation and we normalize this variation by this factor 1 minus gamma. So similarly, we can define the discounted state action variation d pi gamma. So which is the combination of d pi and the target policy pi. So with this normalized discounted state variation, we are able to rewrite the expected total reward eta gamma pi in the form of expectation. So basically, it's just the expectation of the reward function with respect to the state action distribution. Similarly, we can do same thing for the average reward metric. So we first need to define this stationary distribution d pi 1. So we need some assumption to make sure that this distribution does exist. For example, we can assume for any policy pi, the Markov chain induced by pi is always ergodic. Then this d pi s always exists. Similarly, we can define the stationary state action distribution and rewrite the expected reward and rewrite the average reward in the form of expectation. So basically, it's the expectation of the reward with respect to this stationary distribution d pi 1. So now we can see that all our performance metrics is just an expectation with some distribution d pi. But in the off-policy learning setting, our data SI-AI is sampled from an unknown distribution d mu. So here I use d mu to denote any possible distribution. It can be any distribution of interest. For example, if we have a data set, then this d mu is a selection distribution of that data set. This distribution d mu may come from a single known behavior policy, or in a more challenging setting, it may come from multiple unknown behavior policies. So basically the idea is this d mu can be anything and it can be arbitrarily different from d pi. So we do need to assume some regularization on this d mu. For example, we will assume that this d mu covers d pi well, which is not very restrictive. So we not only have SI-AI, we also have the reward RI and the successor state SI prime, which is sampled from the transition kernel P. So here we can see the problem clearly. We want to compute the expectation with the distribution d pi, but we cannot sample from d pi. Instead, we can only sample from d mu. So this is a distribution mismatch problem, which is the major challenge in off-policy learning. So how can we address this problem? Learning the density ratio directly is a promising approach for address this problem. First, we can rewrite this expectation in a different form such that the expectation is taken with respect to the behavior policy d mu, where we can sample from. But of course, if we change the expectation, we need to introduce important sampling ratio to make a correction. So here we have this ratio d pi over d mu, and I will use tau to denote this density ratio. Let's say if we know this density ratio tau somehow, then we can easily estimate this expectation with the sampled data from the behavior policy d mu. We just reweight each reward with the corresponding density ratio, then we can get a good estimation. So here the problem is to learn the density ratio tau. This has been a very active area of research, and there are many interesting works in recently. So most of those work are based on a single equation, this equation. So the idea is that the density ratio satisfies a backward Bellman equation. It's similar, so it's this equation. It is very similar to the Bellman equation if you are familiar with Bellman equation. But the only difference is that in Bellman equation, we have p pi, but in this equation, we have this p pi transpose, which means like the states flow in a backward direction. So that's why I call it a backward Bellman equation. So let's have a detailed look. So here I use D to denote a diagonal matrix, where the diagonal entry is the sampling distribution d mu, and the rho pi 0 is the initial state action distribution. So it's a combination of rho 0 and pi. Importantly, so the action here is sampled from the target policy pi, not the behavior policy mu. Anyway, this is not a major problem because actually we know pi, right? And we use p pi to denote the transition kernel according to the target policy pi. Then we combine them together, we have this equation. And this equation holds for gamma, both gamma smaller than 1 and gamma equals to 1. We need to discuss two different settings separately. The first setting is the discounted setting where gamma is smaller than 1. And the second setting is the average reward setting where we consider gamma equals 1. For the discounted setting where we have gamma smaller than 1, the problem is not very hard because given this equation and given gamma smaller than 1, we can compute the analytical solution of the density ratio tau in. So it has a form like this. So, but obviously we cannot compute this metric production directly. First, we don't know D because we don't know its diagonal term D mu. We can only sample from D mu, but we don't know the analytical expression of D mu, so we don't know D, and we don't know the transition kernel either p pi. So we can't compute the expression of tau directly, but at least this analytical solutions that tau does exist and tau is unique. So we can use some sample-based method to compute this tau. For example, in DualDICE by Nachum et al. 2019. So anyway, when gamma is smaller than 1, the problem is not very hard because the solution to this equation is unique. But when gamma equals to 1, we have some problem. Let's say if gamma equal to 1, then this term will simply disappear. So this equation will degenerate to this one. And similarly, we want to first compute the analytical expression of tau directly. Then we find we need to invert this guy, I minus p. But here the problem is this guy is not invertible. So we all know that p pi is a stochastic matrix. So the largest eigenvalue of this matrix is just 1. So if we do this minus, we can find the resulting matrix has a 0 in its diagonal. So which means it's likely it's not invertible. If this guy is not invertible, it basically means this equation has infinitely many solutions. But apparently tau is a density ratio distribution. So it's the distribution of d pi over the distribution d mu. So it's unique. But this equation has infinitely many solutions. So this is a problem. We need to find other constraints to narrow down the solution space. How can we achieve this? Previous work usually requires 3 constraints for the average reward setting to make sure there is only a single solution. So the first one is the backward Bellman equation, and the second one is a positive constraint. So basically, tau is a ratio. It's a ratio of 2 distribution. So at least it should be larger than 0. So we want to make sure that tau is greater than 0. Here, this is element-wise comparison. And because tau is the ratio of 2 distributions, it should be properly normalized. So we want to make sure that this product equals to 1. This is called the normalization constraint. So in previous work, for example, GenDICE, they implement the first constraint, backward Bellman equation, and the third constraint, normalization constraint, in their objective directly. So they have this objective. So here, this objective consists of 2 terms. The first term is a divergence term to measure the difference between the left-hand side and the right-hand side of the reverse Bellman equation. And the second term is a penalty term to ensure the satisfaction of the normalization constraint. To implement the second constraint, they use special parameterization. For example, when they parameterize tau with the function approximator, or it could be tabular, linear, or neural network, they use special activation function. For example, they use square and exponential. This makes sure that the output of tau is always positive. Mosevi et al. Implement the first constraint in the objective as well. So basically, it's very similar to GenDICE. It's the divergence between the left-hand side and the right-hand side. And Mosevi et al. Implement both the second and the third constraint with self-normalization. So it looks good so far because all constraints are implemented in their algorithms, and the solution and all the 3 constraints together guarantee that we have a unique solution tau that satisfies all the 3 constraints. But the problem is once we use special parameterization, the optimization problem usually becomes non-convex, which means we don't have an effective algorithm to optimize the non-convex objective. So usually we lose convergence guarantees for GenDICE and Mosaic et al. But fortunately, in our recent work, GradientDICE, we find that actually we don't need 3 constraints. 2 constraints are enough. So the Perron-Frobenius theorem says that the solution space of the reverse Bellman equation, the first equation, is 1-dimensional, which means either the positive constraint or the normalization constraint is enough to guarantee that there is a unique solution. We only need 1 of 2 and 3. We don't need both. So we can actually drop 1 and only take 2 out of those 3 constraints. Apparently, the first one is very important and we don't want to drop it. So now let's decide which one to drop, the second one or the third one. So we decide in GradientDICE to drop the second constraint. So this is a positive constraint. We usually implement this constraint by using special parameterization or use projected stochastic gradient descent or use mirror descent. But the problem is all those methods are not very efficient given functional approximation. So we decide to just ignore the second constraint. So this leads to the GradientDICE algorithm. So GradientDICE algorithm has many theoretical advantages over previous methods. For example, in the earliest method of DualDICE, it can only deal with the discounted setting where gamma needs to be smaller than 1. Then GenDICE extends DualDICE to the average reward setting, so it's compatible for both gamma smaller than 1 and gamma equals to 1. But the problem with GenDICE is that it's not convergent with linear function approximation even with tabular representation, it's not convergent. It's mainly because the problem with non-convex due to the special parameterization. And Mosaic et al. Also extends DualDICE to the average reward setting, but still the problem is it's not convergent even under linear function approximation. So in our GenDICE, it's compatible for both gamma smaller than 1 and gamma equals to 1, and we show that GenDICE is convergent under linear function approximation. So here, this is the loss of the GenDICE algorithm. It consists of 2 parts. So the first part accounts for the reverse Bellman equation, the first equation, and the second part accounts for the normalization constraint. And we don't need to implement the second constraint explicitly, because once the first constraint and the third constraint are fulfilled, the second constraint will be fulfilled automatically. So by contrast, GenDICE also implemented the second constraint explicitly. So they have this constraint in their optimization problem. Another interesting thing to notice is that we don't use divergence as GenDICE and Mosaic et al. Did. We use a special L2 norm, which makes sure that we can get samples from the distribution we want. I won't talk about the details about this special L2 norm, but you can check the paper to see why we have to use this special L2 norm instead of the divergence. GradientDICE has not only theoretical advantages, it also has empirical advantages. To see this, we benchmark GradientDICE and several baseline algorithms in several domains. The first one is Boyens chain, which is a classical environment for evaluating reinforcement learning algorithm. So we have this simple markup chain, and we consider tabular representation. So we benchmark the 3 algorithms: GradientDICE, GenDICE, and DualDICE. So the x-axis is the training steps, and the y-axis is the mean square error of the density ratio prediction. The lower, the better. we tested the different discount factors from 0.1 to 0.9 and 1. So the results are averaged over 30 independent runs. We reported the mean and standard error. Importantly, we did a grid search for the learning rate alpha for different algorithms for each gamma. So let's check out the results. As indicated by the red line, we can say DualDICE can't learn anything when gamma is large. For example, when gamma is 0.7, 0.9, or 1, DualDICE can't learn anything at all. This is expected because DualDICE is not designed to work with gamma equal to 1, and it's known to become unstable when gamma gets larger. GenDICE does work for large discount factor, but it's very unstable and it has large variance as indicated by the yellow line. So by contrast, our algorithm, GradientDICE, which is the blue line in the figures, consistently performs well for all the discount factors. We also tested the linear function approximation. The domain is still Boolean chain, and we have different discount factors. The results are quite similar. GradientDICE performs consistently well for all discount factor. And GenDICE usually has a larger variance and is not very stable. DualDICE doesn't work for large discount factor. So nowadays, neural networks have become very popular. So we also tested the GradientDICE with neural network function approximation. We use Mojoko Richer version 2 as our benchmark. So in this domain, we have a robot arm. The goal of this robot arm is to hit a ball. And we use some other control algorithms to train a policy. And we want to estimate the performance of that policy with some pre-given dataset. So similarly, we tested GradientDICE, GenDICE, and DualDICE. The results are quite similar to the results in Boolean chain. So you can see GradientDICE performs consistently well for all the discount factor, and GenDICE is very unstable and has larger variance. So this suggests that GradientDICE has both theoretical and empirical advantages. So here the take-home message is that less is more. If two constraints are enough to guarantee there is a unique solution, we do not actually need 3 constraints. Finally, I want to give thanks for my collaborators, Bo Liu and Xinwen Whitesong. And the code is available in my GitHub. Thanks for joining this talk.